All right, hello and welcome to week 5. We're going to get more into arguments today. So we'll deal with logic at the first half, and then we'll talk about more like human arguments in the second. So here are my goals for you, and let's get right on into it with two topics: deduction and induction. So we should differentiate them. And let me say this just to start off. Deduction is the kind of thing that happens a lot in your computer. It's thinking, it's making choices based on answers that are like always able to be found out. Okay, so computers are really good at this thing called deduction. And then that's an interesting artifact. And then humans are better at induction, or I wouldn't say that computers aren't bad at it, because there's machine learning and data science things, programs that deal with induction all the time, but it's kind of a human concept, induction. It doesn't really have to do with truth. More human-y, if that makes sense. Let us see some examples, and that will hopefully drive home this concept. Please be green. So we have arguments with ourselves, other people, our computers, our Scratch programs. What makes our arguments correct? Is it when it's convincing? Like when it sways somebody, that means it was a correct argument? Well, that's not always the case, but I mean sometimes. And maybe it has to do with some idea of truth. Maybe an argument is true, and that makes it convincing. Like, it's impossible for this argument to be wrong. That's another idea. Let's talk about these things. So deduction is a type of argument style that always deals with certainties. Okay, you can always find things that are definitely the case. Okay, and this will contrast with induction on the next slide. So, and this is just a general thing for any kind of argument. We have an argument. It's made up of premises, or premises, and a conclusion. Okay, so you have some stuff, and premise is just a fancy word for assumption. So you're assuming a bunch of things. Here is my premise 1. Here's my premise 2. They are thought bubbles, perhaps. Here's my premise 3. And these are all somehow morphing together to make my conclusion, which is like, I don't know, a rainbow thought bubble maybe. How about that? And hopefully that's convincing. For deduction, the only way that an argument is convincing and deductive, it's when the conclusion is a certainty. Okay, so P1, P2, and P3, they fit together just so perfectly that the conclusion must always be true. Always true. And so this is when you have a correct deductive argument. Okay? You're talking about certainties, and when it's correct, from these premises, the conclusion always holds. It's always true. So here, those are a lot of words, and they're kind of vague. Here's an example of a deductive argument. So here's my first premise. It's sunny in Fresno. Isn't that true recently? So that's my first premise. That is an assumption. So check. We have assumed that. And then we have premise 2. If it's sunny in Fresno, then Lawton won't be carrying an umbrella. Okay, so that's our second assumption we have to make. Okay, so we've made those two assumptions, and now we have to somehow use them and argue the conclusion. And this is supposed to be a deductive argument, so the conclusion should be a certainty. Okay, so Lawton won't be strong, emphatic, declarative. Okay, this is a declarative statement. Lots of D words. Just remember that. Lawton won't be carrying an umbrella. Always. Okay? So, do these premises imply this conclusion is the question. But this is a deductive argument because it's trying to say something that is always the case. It's trying to say something that is a certainty. Lawton, in any case, no matter which universe we're in, he will not be carrying an umbrella. Okay? So I think you would probably agree that this is a pretty good argument, unless maybe I like to use an umbrella to block the sun. Okay, so that is a deductive argument. The conclusion is a certainty. And if that's a little confusing still, don't worry. It will all make sense on this next slide when I give the opposite kind of, with induction. So there's this thing called mathematical induction, which you learn about in computer science or math. This has nothing to do with that. This is a kind of logic. Okay, so an argument is inductive, we say, when the conclusion, it's not a certainty, but it's very likely. Okay, do you see the difference? Huge difference between a certainty, like won't, and a very likely kind of idea, like with high probability. This is like the weatherman is making inductive arguments. Okay, so for example, I don't know, my neighbor has a dog, and every time I've walked by that dog, it has not tried to bite me. Okay, so that's my premise. So it's an assumption that I have to make to argue my conclusion with. So that's something that's information I need to have to make this make sense. So then my conclusion, based on this premise, this assumption, is, okay, so the next time I walk by that dog, it won't try to bite me. Okay? So this is, I hope you can tell that it's a bit different. It probably won't try to bite me, is probably what I should be saying here, to just drive the point home. But we're talking about not a certainty anymore, we're talking about something that is likely, okay? And yes, I think probably is necessary here, so I should include that, okay? So maybe in like 99% of all the cases, the dog will not try to bite me. But maybe the dog's having a bad day. In that 1% of cases where I walk by that dog, it bites me. That makes this an inductive argument. We're dealing with probabilities. We're dealing with likelihood. Okay? So maybe I should write probabilities, just to remind you when you come back to study this. Okay, so that's deduction and induction, and we can talk about arguments now that are both deductive and inductive. We've seen examples. We can talk about whether they're good. Okay, so here are some ways to discover whether or not arguments are good. We can talk about the validity of an argument, which has a certain meaning, and then soundness is a different kind of way of talking about an argument. So soundness is stronger than validity. If I want you to get anything out of this, that's what I want you to know. So this is stronger than validity. And so this is, we can use these two terms to go and attack an argument. All right, so we want to attack an argument in a logical way. We don't want to say, yeah, you just suck. I don't trust you, so I'm not going to believe you. No, we can have a logical method to tell somebody that their argument is horrible. And that's exactly what we want in this class. Okay, so let's talk about validity and soundness now. So we have an argument. We'll say that it's valid if it's impossible for the premises to be true and the conclusion to be false. Okay? So keep that in the back of your mind and contrast it with this idea of soundness. So an argument is sound if it's valid and all the premises are true. So validity is a necessary requirement for soundness. Okay, so soundness is stronger. So if it's valid and all the premises are true, then we say that an argument is sound. Okay, so here is, I'm excited for this moment for you because in every like philosophy or logic class, this is like the example sound argument that they give to everybody for their first time. So this is exciting. So here is a sound argument. So my first premise 1, all men are mortal. Okay? That's an idea, talking about every single man or woman, every single human. We are all mortal. Okay? that is the premise. You have to, if you want to believe the argument, you have to believe that premise. And then Socrates is a man, premise 2. Okay? And there's a little line here, you can imagine, that separates the premises from the conclusion, because this is the conclusion here, with a copyright symbol, I guess. And so the idea is, this is a sound argument, because is it the case that all men are mortal? Yes. That's pretty true. I don't think we have any, like, I don't know, like, deathless people in the world. We are all mortal. We must accept that. And then premise 2, Socrates is a man. I think we can make a pretty good case for that. We have at least Plato. If we trust him, we can assume that Socrates was totally a man, and he existed. So our conclusion then is, therefore, Socrates is mortal. And that follows from this idea, all men are mortal, and we said that makes sense. Every man shall point to a man, he's totally mortal. And we're pointing to Socrates now, and we're using those two ideas to prove that Socrates is mortal. That's our argument, okay? And it's sound because all the premises, it's sound because the premises are true, and they imply the conclusion. It's impossible for the premises to be true and the conclusion to be false, because this idea plus this idea, it's like we stick Socrates into the man part. He's just one man. So, and if all men are mortal, Socrates is another man, he's totally mortal. Okay? That's the idea. And we'll formalize this a little bit more in a second with the idea of implication. But that's the idea. So this is a sound argument because, yes, Socrates is mortal because all men are mortal and he's a man. Okay? It follows. All right. That was a lot of words. I'm going to show you this in symbols in a little bit. But hopefully that idea, just at a high level, it's making sense. So this is a valid but unfortunately unsound argument. I love Hamilton. So here's my first premise. Everyone who watched Hamilton enjoyed it. Okay, so this is making a case for you point to a person, everyone, you point to a person that watched Hamilton, and it's always the case that that person enjoyed it. Okay? So that's my first premise. To believe my conclusion, you have to accept that. Okay? Then my second premise, my second assumption is John watched Hamilton. Okay? And remember, there's a little line here between the premises and the conclusion. And the idea is, we're trying to argue that, yeah, John must have enjoyed Hamilton then. Okay? So this is a valid argument because the premises, if the premises were true, then the conclusion had to have been true. Because, again, just like this one over here, we're making a case for everyone who watched Hamilton, and we're plugging John into that because he's just another person. So John's one of the everyone who watched Hamilton, and we are saying through this premise that everyone point to a person they enjoyed Hamilton. Okay? So it follows from those two premises that John must have enjoyed Hamilton. If we are to accept these two assumptions, it is always the case that the conclusion follows. Okay? I hope that makes sense to you. Again, I'll show you this in symbol form later. So it must have been the case that John enjoyed Hamilton then. And this is a valid argument, totally valid, because we just noticed that it's impossible for the premises to be true and the conclusion to be false. The issue is, the premises are not all true. I have a feeling that there's at least one person in the world who watched Hamilton and didn't enjoy it, and that makes this premise false, okay? There's somebody who watched Hamilton and was unhappy, okay? So that means that this does not hold, which means we can't use this inside of it, and that means we can't use the whole thing to prove our conclusion, okay? It's like a domino effect. Once one piece falls, there's no hope for the rest, okay? So I hope you see, just from a bird's eye view, the difference between validity now and soundness. And now we can talk about those things, okay? And just in the back of our mind, there's always this concept of truth, okay? So I guess you have to believe what's true, or have a concept of truth in the back of your mind. Okay? But hopefully it makes sense. So here are some examples, and I really encourage you to pause this video and think about them for a second, and we'll come back and discuss them. Okay, so take a second. Is this argument valid or sound? And remember, always the last line is the conclusion. Okay, there's like a little step that separates. Okay, so premise 1, all birds can fly. Premise 2, bats are birds. Boop. Therefore, bats can fly. All right? So first of all, we know in the back of our mind that yes, bats can fly. But that has nothing to do with this particular argument. Okay, I want you to see that. This is we pretend you're an alien, you landed on Earth, you have no knowledge of birds or bats other than these two statements. That is what it means to have. That is what this argument means. We can't pull in extra information like, yeah, I watched bats on the Discovery Channel, they can fly, totally. We can only use these things to prove this thing, okay? That's the idea. So, is this a valid argument? And remember what valid means. It's impossible for the premises to be true and the conclusion to be false. Okay? Well, all birds can fly. That's saying, give me a bird. Let me write down what I keep saying every time when we use the word all. Give me a bird, point to one. If you give me one, then that bird can fly. Okay, that's the idea. All birds can fly is essentially the same as this. Point to a bird, please. It's true that that bird flies. All right? We're kind of singling one out. And so then this one, bats are birds, well, we can kind of plug that in to this. It's like an outlet. And it makes things true. So based on this, well, I'm going to give you a bunch of bats. And we can use those two arguments because bats are birds and birds can fly. Therefore, bats can fly. All right? So that's a totally valid argument. Yes? I hope you see that. These two, it follows from this that bats can fly. Okay? Now, this is not, however, a sound argument. Maybe I want to use red to imply that. This is not a sound argument because I think you can give me a counterexample to this one. And a good way to disprove things is to find a counterexample. So what's a counterexample to that first premise? Our good friends, the penguins. Okay, so because this first premise is not true, it's impossible for it to be sound, because all the premises needed to be true, and also needed to be valid. Okay, so that's the idea. I don't know enough about bats to remember if they are actually birds, but I'm just going to assume that they are. Okay, so this is a valid argument, but not a sound argument. Isn't that cool? There's a difference. Okay, how about this one? All cats are mammals, all dogs are mammals, therefore all cats are dogs. Okay? Do these two premises together imply this conclusion? First of all cats are dogs. I don't think so, right? This is saying all cats are mammals, so yeah, give me a cat, I know it's a mammal. All dogs are mammals. Give me a dog, I know it's a mammal. I can't use any mammalian information to prove that cats are dogs. I know that they're both mammals, but I don't know anything other than that, given these two things. And again, it's always about what you're given. So this is like the world. This is the universe that you get to use right now. It's like you're an alien, you know nothing about cats, you know nothing about dogs other than these two statements, okay? You can't pull in outside information. We're just talking about this argument, and this argument exists in a vacuum, okay? When you're determining validity. So, this is not a valid argument because the premises don't imply the conclusion, it doesn't lead logically to that, and also it's not sound because soundness requires validity, and it's hopeless if it's not valid. Okay? So I hope you see that. And we can knock a few more out now. So, valid or sound? Again, it's always the last thing that's the conclusion, and I always make a bad line the first time. There we go. So if someone was a philosopher, then they weren't a historian. Alright, so it's like, point to somebody, prove to me, like show me their badge, their philosopher badge, then I'll show you that they are not a historian. That's the idea. So if somebody's a philosopher, then they weren't a historian. Okay? And Socrates wasn't a historian. And then the conclusion is, therefore, Socrates was a philosopher. Okay? So do these two things follow? And this one is tricky. This one will make more sense when we talk about implication. But I will tell you why I do not buy this. Okay? I don't think it's valid. So this is saying, if someone's a philosopher, so give me a philosopher, then they're not a historian. Okay? I gotta write tiny, sorry. There we go. Then they weren't a historian. So it's kind of, you can go in this direction. Show me that somebody's a philosopher, then they're not a historian. Okay? And we know that Socrates wasn't a historian based on this premise. It doesn't matter if it's true in real life. We're talking about validity right now. We're caring if the argument itself is valid. It has nothing to do with soundness yet. We don't care if these are true premises. We just care if they logically imply this conclusion. Okay, so this is kind of like a one-way street. If you have a philosopher, you know that they're not a historian. But this way, we're kind of trying to go backwards. Socrates wasn't a historian. We're trying to go this way, and the arrow only goes one way. Okay? So we cannot go in that opposite direction. There are ways to do it, but I don't think that this is the case. Okay? So we can't go backwards like that, and that is why I don't think that this is a valid argument. So therefore, Socrates was a philosopher. No, that doesn't make any sense, because this is a one-way street. If someone was a philosopher, then they weren't a historian. Maybe if we knew that Socrates was a historian, then we could prove that he wasn't a philosopher. That would make sense, and I'll show you why later. But this is kind of a one-way kind of place to go, and we can't go backwards. Okay? So this is a not valid argument. And so, of course, it's immediately also not sound. Okay? So it's getting a bit more tricky. Try and draw out your arrows like this when you see ifs. If you ever see an if and a then, it's an arrow. Okay? And we'll talk about that in just a few slides. Okay, one more. Valid or sound? All computer scientists like to dance salsa. That's our first premise. Some men are computer scientists, our second premise. And then our final conclusion is, therefore, some men like to dance salsa. Okay? And so again, this has the word all in it. So it's like, point to a computer scientist. I will tell you that they like salsa. Okay? Now, the second one is some men. There's at least one man in the world who's a computer scientist. That's what it's saying. Okay? And so we're supposed to use these two together to prove this conclusion. So, the first one, with this first premise, if I assume it, I have one man who's a computer scientist. I think I can use myself. And then I can bring that man into this premise and use it. This is saying all computer scientists like to dance salsa. Well, I just have a man right here who's a computer scientist. So that means he must like to dance salsa, because all computer scientists like to do it. Okay? And therefore, some men like to dance salsa. And the idea is, I just use these two to prove that there's one man who is a computer scientist, that there's one man who happened to be a computer scientist and who liked to dance salsa. Okay? So I know that some men like to dance salsa. I actually know something stronger than this. I know that therefore some male computer scientists Sorry for the small handwriting. I hope that makes sense. Some male computer scientists like to dance salsa, but I'm just proving this simpler statement. And it's totally true. Because I started here, used what I had, used what it gave me, put it into there, and plopped it all out here. Okay? I hope you see the process. Alright. And then, so this is valid. Okay? So, if I assume these two, then I can totally get this. Now, is it sound? Well, is it true that all computer scientists like to dance salsa? That is unfortunately not the case. Okay? That is not true. It is, though, true that some men are computer scientists. Oops, I wanted green. Go back. Oh, now you're green. That is true. But for validity, we need both. We need both of these to be true. Okay? So it's impossible for this to be sound. All right? So hopefully with those 4 examples, it's getting a bit more clear in your mind. But that is where I want to leave us for validity and soundness for the moment. Okay. All right, now let's move on to implication and if. So what does if really mean? We've been using it up here. Let's see here, right here, other places. What does if mean logically? Like, is there a way we can just pin it down mathematically so that we always know what we're talking about? Okay, let's try and do that. So let's pretend our dad says, all right, I'll give you $20 if you mow the lawn. And you say, sure. So under what conditions would you feel cheated if you didn't get that $20? Because we're trying to prove an if statement. So what does it mean for an if to logically be true? Okay? And, well, let's break it down into ways that it could be false. So how could the if be false? So this is what Dad tells us. When would we be sad? When would we feel cheated if we didn't get that $20? Okay? So let's list our options. So here we have mowed the lawn and got $20, and we're trying all the possibilities. Okay? So the idea is we're trying to say something like, if you mow the lawn, then I'll give you $20. Then you got $20. Okay? So if it's the case that you mowed the lawn and got $20, you don't feel cheated because you did the work that Dad asked you to do, and you got your $20 like he said he would give you. Okay? So you don't feel cheated. No, you got your money. Okay, what if you mowed the lawn, but you didn't get $20? Actually, yes, you would feel cheated. Why? Why, Dad, would you do that? So that's the one case where this is a bad thing, and let's talk about the rest as well. So if you didn't mow the lawn, but you got $20 because your dad's just a nice person, then you totally don't feel cheated because you got your money for free, right? So that's nice. So that's okay. And then finally, in the last case, you didn't mow the lawn and you didn't get $20. Do you feel cheated? Well, no, you're just lazy. You didn't do the work, and you didn't uphold your end of the bargain. Okay, so it seems like this is the one case, the true-false case, where something went wrong and the if statement wasn't true. Okay, so this should be how we say things. This should be the false case of an if statement. It should never be true if the premise is true but the conclusion is false. But all the other ones can be true because we don't feel cheated. Okay, so that's a bit hand-wavy, but let's go to the next slide. So implication is the way that we talk about in math the if A then B concept. Okay, and we draw it like this with an arrow. Okay, so if A is true, then B is true. That's how you read it. You can also say A implies B for short. Okay, so let me write this up here. So if A is true, that's how you read it. Then B is true. Something like that. Okay? So that's what this is. Implication is the fancy logical term for if-then. Okay? So in programming, we call this a conditional. You had your if-then-else statement. You also had your if-then statement. Okay? So we know about those blocks already. You had an if block. If it's the case that something was true, then do this thing inside. Yeah? And we just noticed, we noticed the truth table. Okay, so in the true case, if we mow the lawn and we got $20, then yeah, the if statement made sense. It was true. We proved that it was true, that if you mow the lawn, then you get $20. The true-false case was the one case where something went horribly wrong. Okay? So that is the false case of the implication. So if A, then B is false if you can have A but not get B. Because that's the idea of an implication. Okay? That's the one time it's not true. So in order to prove then an implication, you show that it's impossible to fulfill the if and not receive the then. Like you write up a contract with your dad and be like, all right, in this one case, I'm going to feel cheated, and then you didn't uphold your bargain, so I will sue you for those $20. Okay? The alternative way to read this is, if I give you A, then you have to give me B. Okay? That is the idea of implication of an if statement. And it just so happens that this solves a few of our problems from before. It makes it easy to just push symbols around and notice how things work. So here is deduction. And yeah, let's talk about why it's logical. So here is the first idea. Here's the argument from before. All men are mortal, Socrates is a man, therefore Socrates is mortal. All right, let's translate that into symbols, if implications with if. Okay, so the idea of reading this is, I get to assume that man implies mortal. If man, then mortal. So I have this exact truth table. And then I also know that man is true. Okay? Man is true. I have a man right here. He's Socrates. All right? Then I know that mortal must also be true. Because, let me show you the table now because it makes so much sense. If I know that this is a true statement, okay? So that means I'm in one of these three. And I also know that my premise is true, because that's what man is. It's the premise right here. It's A. I know that I have to be in this case, okay? I know that B must be true, okay? It follows from the truth table. Truth table for implication, for if then. Okay? So that is how I kind of want you eventually to think about these kinds of arguments. See if you can break them down into a symbol form, and that will make your life so much easier. Because you can just look at truth tables at that point and know when something is actually the case. So one thing that I do want to do is talk about circuit diagrams again, because it would be nice to prove these kinds of things inside of a computer. Let me show you that it just so happens that if A then B simplifies to, remember we can do anything with and or and not, it happens to simplify to not A or B, okay? And I encourage you to look at this, but it'll be exactly equivalent here, right? Because not A, false, or B is true. Yeah, that's true. Not A or B, oh, false or false. That's the one time it's false. And then not A or B, it's always going to be true because A is false. Okay, so you can now draw a circuit diagram for implication, can't you? What would you put here? What would your many circuits be? Question mark. That end up with A implies B. So think about that, and you have all the tools at your disposal now. Isn't that nice? Okay. Now let's move on to framing, and then we have these two sections left. That'll be it. So, framing. Now, the idea behind this, just very briefly, is that when we make arguments, we argue with some people, they don't believe us. And, well, our argument was so good, though, you know? Why don't they see things the way that we see things? Like, obviously, my point is correct. Why what's wrong with them? It's obvious. So that's where this concept of framing comes in. Okay, so frame or frame of reference, sometimes you might hear it called, it's how you look at a situation. Okay, so this is departing from symbols for a moment. This is another kind of way to think about arguments. So your worldview, your frame of reference, it's how you view a situation, how you think about something. Okay, so and it's going to shape how you view the world. Okay, so it's your worldview, we can say. Your worldview. It's what you believe, perhaps what your parents believe, things like that. Your setting, like the place you are in the world determines your worldview. That's the idea. So that is what a frame is, and if you can control that frame, you can win an argument. You can control the entire argument, okay? Because you can bend something. You can bend an idea to your will at that point, okay? So, and that is the reason that somebody can have the exact opposite viewpoint than you on a topic and still justify it, still make logical conclusions, okay? Because of their frame of reference. All right, so the quintessential example of this is politics, of course, and so I hope nobody gets angry at me. I'm going to give both sides of the idea. Very, very simplified, obviously. But here's essentially some examples of frames in politics. So you got your left-wing people, you got your right-wing people, and the same topic can be viewed in two different ways. You have pro-choice, pro-life, single-payer healthcare, socialist healthcare, all these things, drilling for oil, energy exploration, public service, big government. They all imply something, okay? There's a connotation to every one of these things. And this is why, if you're on one side and somebody's on the other, this is why it's hard to find common ground, okay? Just understand that, and that's the reason behind everything. You can view a situation, you can view something correctly in your mind, but somebody else can have a completely opposite worldview, a different frame of reference, and that is why they don't see your point. Okay, so that's just something I wanted to spell out to you, and yeah, just keep that in the back of your mind. Whenever you want to win an argument, you got to try and bring them onto your side, get them into your frame. Okay, and then with that, let's move to state machines and then get out of here. Okay, so we have computation. We're kind of spilling the programming into this lecture a little bit. So we have done things. We have breaking. Oh man, that's a fun word. So we've made programs. We're good at that now, and our programs are just going to get larger. So how can we break down computation so that we can like have little bite-sized chunks and then kind of string them together in a nice logical way that gives us our big shiny program that we really wanted, okay? Package them all up nicely and get our end goal. And we've talked about this a little bit. We've talked about algorithms, right? Algorithms. I've shown you algorithms to do specific things. I've walked through my implementations of things with you. And it's all about breaking down a problem into simpler pieces so that we can think about them. Because as humans, we can't keep a lot of stuff. We can't keep the entire thing inside of our heads at one time. So if we can just make some nice chunks for ourselves, maybe that would make things easier. And here is a way to think about computation that might help sometimes, okay? There's this thing called a state machine, and it's really fun, and I think it's pretty intuitive. So here is like a state machine for a human. Let's say that you are born, you start out the day maybe, or something, in a state, okay? So everybody has a state. So you're always in at least one state. Or in this case, you're always in exactly one. Always in a state, okay? You can, though, transfer yourself to new states. You can move to new states. via, we'll say transitions or actions. And like actions take place to move you between states. This is all very vague, don't worry. Let's talk about this one. So you start out at home. That's what this arrow implies. You start out at home, and then it's the daytime. You got to go to work, so you're going to take the train, and that gets you to the work state. You see that? So now you exist in the work state, and assuming you're not working from home, you're going to take the train back, and then you're at the home state again. Okay, you see how you just maneuvered between states? And this is really helpful for programs because you can be in like the request input state, the perform computation on input state, the print state, things like that. It really helps to think about processes in this way sometimes. So now you're in home, and then you're tired, and so you go to bed, and you need to go to sleep to get into the bed state. Okay? And now you're stuck there until your alarm goes off in the morning, and you wake up, and you're still at home, and then the process completes and completes and completes, and you follow these transitions. Maybe it's the weekend, and you just stay at home for 2 days, and you don't go to work until the weekdays. But I hope you can see how you can maneuver yourself, move around inside of these things called state machines, and they help you with computation, because here's like an idea for Uber. If you can read this, maybe I'll make it a little bigger. Uber or Lyft, back when they were things. Let's do one thing right now. We're going to bring you to front. Okay, so let's say that we are in a certain state, like our driver is in a certain state maybe, but we use the Lyft app. We request a trip, and now we are sitting in the trip requested state. Okay? And then we can move around. We first have to pay before the driver is available to us, which makes sense. So then we're in this state after we pay. Okay, you see how we're moving around. And if it failed, we have to try and request a trip again on a new card maybe. Okay? So we are like somebody who's taking a Lyft or an Uber. And so now we just paid. We're in the driver assigned state, but we're not in the car yet. And then the car shows up, and we're still in the driver assigned state. Okay? Because the driver, like this is the program that's keeping track of which drivers can process new customers. Okay? So we're in the car. Then finally, our trip is over. Okay? At that point, the driver is unassigned, and there's some code that has to work on that, and then the trip is over. Okay? And not really sure how you can get to this state. Probably you can press the cancel button from the driver assigned state, something like that. But I just copied this from the internet. But I hope you can see, like, pretend that you start out and you want to find a Lyft. That's how the Lyft program or the Uber program, the app, is going to bring you between its states of code. Okay? So that is a state machine. And it's useful. With that, let's bring you to the back again. There we go. With that, I want to show you a few more examples of this. So just to drive it home in your head. And you can use like variables in your programs to keep track of which state you're in. And then like input can transition you between them. Okay? So maybe as a student, I think of you as a two-state machine. You're in a learn state or a practice state, for example, and you alternate between the two when I assign something or I post a lecture. So your initial state was learn. You came to this class ready to learn, and I gave you stuff to do to further your knowledge, okay, to practice the knowledge that I gave you. All right, so then you're in the practice state. And so while maybe you can keep coming back to the practice state, stay in it as long as the assignment's not finished. And then once I post a new lecture, maybe, you can go back to the learn state, okay? And you keep watching the lecture. Maybe you have dinner, come back, watch the lecture some more. And then you can finally practice some more after I assign a new assignment. Okay, so as long as you're not done, you stay in the same state, for example. And there's a concept of final state as well. So when you put two, that's like a double circle, it's called a final state. Because at the end of the class, you will have practiced on the final exam, and there's nothing more for me to teach you. And so you end this class in this state. That's the idea. So you start the class in this state, start state. And you end the class in this final state, if that makes sense. And with that, I just want to give you one last example, and I'll redraw this. But this is how you can make this into a program. Actually, this would be a lot easier if I did the little lasso. Come on. Yeah. Okay. So I want to count the number of words in a string of characters or in like a sentence. So how do I want to say this? In a sentence. So I have a program, and I got a variable from the user asking me to enter something like answer. And the user entered maybe their name, or hi mom or something, exclamation point. And maybe I should make that longer, but we'll see how this works. And the idea is we can use a state machine to count the number of words in a variable that holds characters. Okay, so we'll count the words in a sentence that a user entered with a state machine. And the idea is we can walk through each character. Maybe I want to move this down over here. The idea is we can walk through each individual character in this sentence. We can say, we can start at the H and be like, no, I haven't seen a new word yet. And then we can, oh no, I would like to be able to do this. What if I make an arrow over here and just drag, yeah, there we go. So I start at the H, and be like, all right, no new words. Then an I, aha. And then a space, oh, the word just ended. So I've just seen another word. And then the second I see the M, I've seen another word. Oh, I'm still in the same word when I see the O. Oh, I'm still in the same word when I see the M. Oh, I'm still in the same word when I see the exclamation point. And the second that I see another character, I know that I'm in a word. So I started out maybe over here having not seen anything. Then the second I see an H, I know I've seen a new word. I can add to my count of words. And I see an I, I'm still in the same word. I see a space, one word is finished. Then I see the M, and I know that I've got two words now. Okay? And we can just follow this through everything. I'm going to save this arrow, actually. So, I'm not going to try and make you come up with this idea. This was taught to me in my first programming class, but here's how you do it. It's a two-state machine. You start out your state where you're not in a word. That's your start state. And so that's like we haven't read any characters yet. We haven't looked at the H yet. We're not inside a word. The second you see a character, a non-space, you are inside a word. Okay, so you can go from outside a word to inside a word. Whenever you see a non-space character, and at the very beginning. So I saw the H, I know I'm in a word, but then when I still see the next I, I'm still inside that word, okay? See non-space again. Still inside that word. But then the second I see a space, I'm outside a word again. No. I talked and then wrote what I said, and that was incorrect. This is C, a space. All right, and as long as you keep seeing spaces, you say outside of a word. Maybe like you're using a typewriter and you use 2 spaces after every sentence. Okay, so the idea is this is a state machine that represents whether or not you're inside or outside of a word. And every time you see a non-space character, every time you take this transition, you'll add 1 to the number of words that you're looking at, that you think there are. So initially, there are 0 words. Okay? You see the first character, and oh man, was it a non-space character? So now we're inside a word, and we can add 1 to our count. So now we know there's at least 1 word. Okay? Then we look at the next character. It's not a space, so we stay inside of this state. We don't move. Okay? Now we see a space, so we're going to follow this transition to the not inside a word, to the outside of a word state. And now we're ready to potentially see another word and add to our count. And so the second we see a not space character, an alphabetic character, we're going to add 1 to our count. You see how this helps you keep track of kind of a complicated task? It makes it super easy. You just have 2 states and you transition between them. So now I've seen my second word, and now I'm just going to keep seeing non-space characters until I get to the end, and I know for a fact, because this is a correct state machine, there are ways to prove that, but that is a graduate level topic, I know that this is a 2-word sentence. Okay? So that is how to use a state machine to do something that would be useful as a programmer. All right. I think that's where I want to leave us. And yeah. So with that, I will see you next time.